Good evening, everyone, and welcome to the seventh live session for the course Introductory course in Real Analysis. So, in today's session, we'll be discussing about limits of functions. That is the main aim for today. So, to begin with, let's look at this problem. Okay, so this is the function x square and root x. Okay, so for positive c, so c is positive over here. So, you have to prove that as x goes to c, the function x square and root x converges to c square and root c corresponding respectively. Okay, so so the first thing is why we need to take root c, c to be positive. So here c has been chosen positive just for one reason, because here you want to define root c, correct? And so one more thing is that when you're looking at this limit, okay, so I'm talking about root x. So when you are talking about this limit, so it tells you that what is the behavior of root x. So what is the meaning of limit? Limit basically means that what is the behavior of the function in the neighborhood of that point, right? So over here, when you are talking about this limit, so you can think that x could be negative as well. So for example, if I choose c to be, let's say, 0.1, then you can say when x is going to 0.1, then it includes negative point. But when we are talking about limit, we just only need to care about in a very small neighborhood of this point c, right? So over here, when you have to look at limit x going to c, that means you have to look at the behavior of the function in a very small neighborhood, c minus epsilon to c plus epsilon, okay, in a very small neighborhood. Now since c is positive, okay, so you can obviously choose epsilon to be c by 2. So if I choose epsilon to be c by 2, this would be c by 2 and then 3c by 2. So clearly these are positive, each of the points. So this is subset of 0 comma 1 or 0 comma 2c, let's say, right? So over here also this root x will make sense, because we are talking about limit as x goes to c, and c is positive, so root x will make sense. Okay, so that was just one small remark before we start to solve the problem. So the first thing is that, okay, this problem makes sense. Okay, so everything is good over here. So now the question is how to prove this. So you know that these functions, this is very obvious to you, but over here we will be trying to establish this result using the definition of the limit what you have seen, right? So let me, I should give some I should give the definition first. So let me say, so suppose f is a function. Okay, so let's say f is a function from interval, let's say, or it could be in R. So let's make it from R to R, be any function. Okay, so suppose, so limit x going to c f of x equal to L. So what does this mean, right? So this basically means that the function fx is very close to L. So okay, so I'm writing the meaning of this. Okay, so this means for any epsilon greater than 0, there exists delta greater than 0, such that this function fx is very close to L, is epsilon close to L. Okay, so this epsilon is in your hand. So how much close you want, you can choose. Okay, but corresponding to this epsilon, there will exist a delta, such that this will be true if x is in this dilated neighborhood of c. Okay, so what does this mean? This means that x will belong to c minus delta to c union c to c plus delta. Okay, so you just remove the point c because you don't know whether, okay, so over here I have written from R to R, but okay, it could be any function. Okay, so let's not put R here. Okay, so suppose f is any function given some domain and some codomain. Okay, so f is any function, let's not talk about domain and all. So f could not be defined at the point c, that is why we just delete the point c. Okay, and then we ask that, okay, if you remove the point c, so that means if this is the point c, this is c minus delta, this is c plus delta, So if the point x is in this area or in this region, then the function is also close to L. So if you want to look at the picture, maybe I can draw some. So suppose this is sorry. So suppose this is your function. Okay, you don't know about C, so C I'm putting hollow, and then something else. Okay, so the function is okay. So over here, let me put it in a continuous way. Okay, so this is the function, let's say. Then the point is that limit of this function would be this point. So let me draw this y-axis. So this is x, this is y, this is your function y equals fx. Okay, so suppose this point is L. Okay, so the thing is that this, and the limit is given to be L. So this definition is telling you that if you choose in this neighborhood, okay, then the function, okay, let me make it a bit bigger. Okay, so it says that if you want, so epsilon is in your hand. So suppose I gave you this epsilon. Okay, so L minus epsilon to L plus epsilon. So this is, so you want the function to be close, epsilon close to this L. Okay, so corresponding to this L, you can see that you are getting delta here, right? This delta, okay, such that when your x lies here in this domain, then the function is also in this interval, right? So L minus epsilon to L plus epsilon. So this is what it means. So now if you reduce your epsilon, so if you reduce the size of the epsilon, then correspondingly there will be reduction in, so there could be expansion also, but let's not say that it will reduce, but we will get another delta. Okay, so this is C minus delta 1, C plus delta 1, if your epsilon 1 is this one. Okay, so this is L plus epsilon 1. So corresponding to each epsilon you will get a delta. That's the main thing about this limit. Okay, so that's all about the definition. So this is the mathematical statement, and this is how you can understand by pictures. Okay, so now let's go to the problem. So over here you have to prove that this limit is C square. Okay, so let's try to solve the first one. So as I mentioned that you have to choose any epsilon. So we'll first write, okay, let epsilon greater than 0 be any arbitrary number, right? Okay, now you want to estimate this difference, that how the function is close to the limit value. So over here the limit is given to be C square, and this is the function. So you want to basically estimate this x square minus C square, right? So you want this quantity to be less than epsilon if your x is in some delta neighborhood of C, right? Because this is your C and this is your the limit L. So this is L, this is your C as above. Okay, so this is now you can write this as x plus C and then x minus C. Now this is equal to mod of x plus C mod of x minus C. Okay, so now see, this is what you want. So you want to give some restriction on this value, so that, so you want to this one to be very small, so that this whole quantity becomes very small, right, as you want. Okay, so what we'll do, so this is something that is very useful to us, so we'll keep it as it is. Now we'll try to deal with the other term. So now we can use the triangle inequality, and we can say this is mod x plus, so C is positive, so C and then mod x minus C. Okay, so let us say this is some star. Okay, now the question is that you have to remove this term somehow. Okay, because x is not a very good, it does not look good over here. So if you replace this term or bound this term by some constant m, then you are done, right? So if I bound this by some constant, then clearly this would be less than epsilon if my x minus C is less than epsilon by m, right? This is very obvious. So now the question is how to determine this m. right? So what we'll do now, so this is very actually simple, there's nothing much to do. So what you can say, so see, when you are talking about limit, you just have to look in the neighborhood of C. So that's the only thing what will help us to get some bound for this mod x plus C. Okay, so what we'll do, so consider x, okay, such that mod of x minus C is less than 1. That means you are considering the point x from C minus epsilon to C plus epsilon. Okay, that is x belong to C minus 1 to C plus 1. Now when you choose this x from this neighborhood, then mod of x can be written as mod of x minus C plus mod of C, right, just by triangle inequality. Then over here you can write this as, this is less than 1 plus C. Okay, now what you do, so now from star you have mod of x square minus C square is less than 1 plus 2C and then mod x minus C, correct? So again, now this is the m what I was talking about earlier. Okay, now you know that this will be less than epsilon if mod of x minus C is less than epsilon upon 1 plus 2C. Okay, so see, you have put two restriction on the range of x, like what value x should take. So the first restriction was that x should belong to this, okay, and the second restriction is that x should satisfy this one. Okay, so what we'll do now, we'll take the minimum of these two quantities. Okay, so now define delta to be minimum of this one, right, this one, and this epsilon upon 1 plus 2C. Okay, once I choose my delta to be this, then for 0 less than mod x minus C less than delta. Okay, so when I am choosing the minimum one, that means it satisfies this and it satisfies this as well. Okay, so both of the conditions are satisfied. This we have, so we'll have the final answer, which is x square minus C square is less than epsilon. Okay, so we have got that when x, so we have got one delta. Okay, so corresponding to this epsilon, so we have chosen epsilon arbitrary, so epsilon was any positive real number, and corresponding to that positive real number we have got delta, which is minimum of 1 upon and epsilon upon 1 plus 2C, right, such that this holds true, that is mod x square minus C square is less than epsilon. Okay, so this proves limit x tending to C, x square is C square. Okay, so this was about the first problem. So this is how we can prove this first result. Okay, now let's come to the second one, which says that limit x going to C, root x will be root C. Okay, again we'll try to do in a similar way. Okay, so again we'll write let epsilon greater than 0 be any real number. Okay, and then what we have to estimate, so remember this is my fx and this is my L, right, as per this definition. So I'll write mod of fx minus L, so I'll have to estimate mod of root x minus root C, right. Now I have to show that this is very small or less than epsilon if my x is in some another neighborhood, that is if x is close to C, then my fx is close to fc, then root x is close to root C. Okay, so we will try to do that. So let us try to see how we can do this. So remember, as in the last class, we would, if we can get this x minus C, then that would be very good. because from there we'll get the restriction on x. Okay, so similarly what we'll do, we'll try to get this mod x minus c. So for that we need to do the rationalization. So what I have is root x minus root c. So I'll multiply this by root x up plus root c and then divide by root x plus root c. Okay, so now in the numerator we'll have x minus c, and in the denominator we have root x plus root c. Correct. So again we have reached at a similar kind of situation. So again what we would like to do, we would like to remove this x, right? That should be our goal. That if we somehow get rid of this root x, then we are done. Correct. So we know that over here, so you see, as I was mentioning before, that since my c is positive, so I can assume my x is also positive. Okay, so what we'll do, so for x greater than 0, okay, this root x plus root c is greater than or equal to root c, or just strict, then I can have, then root x minus root c is less than 1 upon root c mod x minus c, right? Okay, I think again there is some lag. Okay, let me just switch off my video probably. Okay, now I think it's bit better. I don't know. Let's see how it becomes normal. So far, like, this is what I have said, that root x minus root c is less than 1 by root c into mod x minus c. Okay. Now, so as I mentioned earlier, this x I can choose to be strictly greater than 0 because we have to look at the neighborhood of c, right? So since my c is greater than 0, I can look at some small neighborhood. So I am restricting that my x is also greater than 0. Okay, that's it. So then we have this bound. Now we can move further. So now this is less than epsilon if mod x minus c is less than root c times epsilon, right? So if my mod x minus c is less than this, then this is true, that this would be less than epsilon. Okay, so what we can do now is, okay, so we have to make one thing sure, that this thing, okay, so let me write what this means. So this means that, so what does this mean? X minus c root less than c times epsilon implies that this is c minus root c times epsilon, this is x, and this is c plus root c times epsilon. Okay, note that root c, okay, is always going to be less than c, right? So this term on the left is always going to be positive, okay, because epsilon is very small, so you can assume that epsilon is less than 1, right? So you can say that, so how to prove this? C minus root c epsilon. So okay, first let me write epsilon is less than 1, then this would mean that minus root c times epsilon is greater than minus root c, and this would imply c minus root c times epsilon is greater than c minus root c, and this is positive. Okay, so we are in a good state. So this restriction what we chose is actually true with this condition, so this is compatible with the earlier one. Okay, so this was just a remark. So this was possible just because c is positive. Okay, then this proves, so this is my delta, right? So if my mod x minus c is less than delta, then this root x minus root c is less than epsilon, and this fulfills the definition. Okay, so this implies, or this means, this proves limit x going to c root of x is equal to root of c. Okay, so fine. So this was just to recall you the definition, how to use the definition. So I hope this is clear to everyone. Is it okay or is there some doubt? Okay. Okay, so now let's move back to the second problem. So over here, like we have a few statements given to us. Now we have to check whether the following are true or not. Okay, so let's start with the first one. Okay, so you tell me the answer. Okay, so you know already that if limit x tending to c fx exists, so let's say this is L, and if limit x tending to c gx is exists, let's say M, then you know that the limit of fx plus gx will also exist, right? And this would be L plus M. This is very easy proof, like you just have to use the triangle inequality, that's it. So you know this result. Now A is some sort of converse of this statement, where you have been given that the limit of sum exists. That means limit x going to c fx plus gx exist. Now the question is, does this imply that limit fx or limit gx will exist? So is it possible that, is this always true that one of the limit will exist? So what do you think? Yeah, any guesses? Nothing? Okay, so the statement is false. Okay, so now the question is how to give the counter example. Okay, so when I say that the statement is false, you have to look for a function for which the limit will not exist, right? So what we'll do, so let's choose one function. So this is the A part. So I'm defining this function f. Okay, so like this maybe. So f of x is, let's say it's something 2x greater than 0 and 3 when x is less than 0. Okay, so that means the function is like this. So it is 2 in this region, so this is 2, so this is 3 in the negative side, so this is hollow and this is this. So clearly you see that the left hand limit is going to be 3 and the right hand limit is going to be 2, right? So the limit is not existing, I mean limit does not exist. Okay, so this maybe I'll leave it to you. If you want to check by epsilon delta definition, that you can check, but over here it's very clear. So clearly limit x going to 0 minus f of x is 3 and limit x going to 0 plus g of x is 2, and clearly they are not equal, right? So this implies limit x going to 0 f of x does not exist. Very good. Now the question is, you have to find g as well. So you have to find one more function for which the limit will not exist, but you have to choose it cleverly that the sum becomes a good function. That means for the sum the limit should exist, right, to get the counter example. Now what do you think, what should I choose my g to be?
Minus 2 if x greater than or equal to 0 and minus 2.
Yeah, correct. Your guess is Completely right. So you just take minus x greater than equal to 0 and then minus 3 x less than 0. So again this limit x tending to 0, g of x does not exist for the same reason. But if you look at the function f plus g of x, this is going to be 0 for x belonging to R, right? So it's constant. So clearly this limit x tending to 0 f plus g of x is going to be 0 because it's a constant function, so nothing to worry, right? Okay, so this was about the first one. I hope it's clear to everyone. Okay, now let's come back to the second question. So over here again the question is similar to what you have seen. So you already know that if limit fx exists, limit gx exists, then the limit of the product will also exist, and that would be equal to the product of the limits, right? This is what you have seen. Now the question is again the converse, that suppose that the limit of the product function exists, does that imply that one of the limit will exist? That means limit fx or limit gx will exist. Again, what do you feel? Any guesses?
Not necessary, sir.
Not necessary, right? So it's going to be a false statement. So
Yeah.
can you cook up some counter example?
The same example define f of x to be 1 by 2, 1 by 3, and the g of x to be 2, 3. So it will be a constant function to be 1.
Correct. Very good. So you are completely right. So we'll do f and g, f as above. Okay, and I'll change the definition of g as g of x. I will make now 1 by 2 for x greater than equal to 0 and 1 by 3 for x less than 0. Then this would imply that f g x is going to be a constant function 1, right? So again this limit will exist, right? So this is obvious. Okay, so I'm not going to the detail. Now let's come to the third part. So the third problem is that suppose that the limit mod of f exists, will that imply, so you have seen this thing, right, that if the limit f exists, then the limit of mod f also exists, right? Again, just by triangle inequality, the proof, you can prove it. So the converse is true, obviously. Converse is true. Okay, let me write this. So limit fx x tending to c is L. This implies that the limit x tending to c mod of fx is mod of L. Right? This is what I've seen. The question is the converse. Again, what do you feel? There could be. Okay, first you guess, then I'll tell.
This is also false, sir.
This is also false, and you can cook up the similar kind of example, right? Can you tell me
Yeah,
what the
minus
example?
1 and plus 1.
Correct. So define fx to be 1 when x is greater than equal to 0 and minus 1 when x is less than 0. Again, the limit will not exist, right? The function. But if you look at the mod f x is going to be a constant 1, right? So again, you have this counter example. Okay, now let's move to the next one, which is D. So you know that when the limit f exists, the limit f square will also exist, and the limit value will be just L square, right? Now the question is converse. What do you think?
can take x into sine 1 by x.
Sorry, f to be
X into sine 1 by x.
sine 1 by x. So you are saying that f square, okay, I can.
No, f for the function f into g,
Mm-hmm.
x into sine 1 by x, f of x equal to x and g of x equal to sine 1 by x.
No, no, but now the question is this one, that the limit f square exists, but limit f does not exist.
Okay.
So about the d part.
So now I'm thinking about E, option E. Okay.
Oh, okay, you are talking about option E. Okay, so we'll come to that, okay, in a moment.
Okay.
But I think this the example what you gave is also going to be true uh, when, like, if you look at this, just a second. So x sine 1 by x is bounded, so no, the limit will be 0. This limit will exist. So mod x sine 1 by x is less than equal to mod x. This is less than epsilon. So this limit exists in this case. Okay, so this cannot be, but you can take the same example as C. Okay, so the answer is that same as C. Because if you take a square, it's basically a constant function, but over here the limit is not existing. So f square limit exists, but the limit of f does not exist. Now coming to your E part, so I'll look at the questions. Fx is x is sine 1 by x. Okay. So the question was that this limit fx gs exists. Okay, so there is a difference in this B part and E part. So you have here one more assumption, that one of the limit exists. Okay, so the product limit exists, one of the function limit exists. Now the question is, does the other limit also exist? Okay, so as she has mentioned, so this is my fx, this is my gx. So clearly gx is defined for x not equal to 0, right? Okay, so the range or the domain for this g would be r minus 0, and for this f it is r. Okay, so this fgx is going to be x sine 1 by x for x belonging to r minus 0. So what is your C here?
C equal to 0.
C will be 0, right? Okay, so this limit x tending to 0, fgx is going to be, what will be the value? I think I already mentioned it. So it's going to be 0, right?
0.
And the answer is, this is a simple estimate. So mod x sine 1 by x equals to 2. So sine x is bounded by 1, so you can make it x, and this is less than epsilon if 0 less than mod x is less than delta, which is epsilon, right? So this proves that this limit is going to be 0, and limit x tending to 0, f of x is 0, but limit x going to 0, sine 1 by x does not exist. Okay, now can someone prove that this limit will not exist? Do you have any argument to prove this?
So we can take two different sequence.
Okay, you are talking about sequential, okay?
Yes.
So what sort of sequence will take?
1 by n pi, xn equal to 1 by n pi.
Correct.
Then yn equal to, other one is 1 by 2n plus 1 times pi.
No, that won't help, right? Because that is again going to be 0. So I think what you mean is basically odd multiples of pi by 2.
The odd multiples.
Yeah, correct. So it's
2n plus 1
pi by 2.
into pi by 2. Yes.
Correct. So we know that this also goes to 0 and this also goes to 0 as n goes to infinity. But this, if you look at sine xn, this is equal to 0 for all n, and sine of yn is going to be 1. It's going to be plus minus 1, so it's better to take so 3 pi by 2. No, over here it will be 3 pi by 2 and then we'll have pi by 2. So it's going to be oscillating. Just a second. So
Or we can take 4n plus 1 by
yeah,
2.
exactly, that's what I'm thinking. So better change something like this, right? Then it's going to be 5 and the next one would be 9 pi by 2. So it's basically going to be 1, right? So for all n, correct? Okay, so we have got two sequences which are converging to 0, but their corresponding functional limit is going to 2 different points. So this tells you that the limit x going to 0 sine 1 by x does not exist. Okay, very good. So this was quite complicated example. Okay, so it could be, I mean, you can even get a simpler example if you want. So maybe I'll now tell you one simpler example. Okay, so this is one of the example. Or just you can look at this. So you have to first choose one function whose limit does not exist, right? So you basically go with anything like before. Okay, right? So this, you just like previous one, we have chosen one function. Now the thing is that if you multiply any function by 0, you are going to get 0. Okay, so what I'll do, I'll just define my next function as 0. So clearly this limit exists. Okay, just a second, whether it was f or g, because you change it a bit, maybe you make it as g and this as f. So clearly this limit exists, and now if you look at the product, this is going to be 0. So clearly the limit for this and limit for this is going to exist, but the limit of this does not exist. Okay. Okay, so we have got 2 examples for this case. Okay, so was everything okay till now? Do you have some doubts? Okay, so now let's move to the next problem. So over here you have to check whether the limit for this function x plus sine x exists or not. Okay, so you know the definition of sine function, right? So sine function, the sine function will tell you the sine of the x, right? So it's going to be 1 if x is greater than equal to 0, greater than 0, 0 if x is equal to 0, and minus 1 if x is less than 0, correct? So you have to tell whether the limit of this will exist or not. Okay, so let's if you want, you can check. Okay, so let me define the new function itself. So you write this as x plus sine of x. So this is going to be x plus 1 if x is positive. It is going to be 0 for x equal to 0, and then x minus 1 for x negative, right? Okay. So there are two ways basically. So let's look at this one way, which is the direct one. So you can clearly see this limit x tending to 0. If I take it from the right side, okay, for fx, what will you get? You'll get 1, right? So for x positive you have this value. So when you take x going to 0 from right, you will get 1. But when you take from left, it is going to be minus 1. So clearly they are not equal, right? So this implies that limit x going to 0 f of x does not exist, correct? So this is the obvious solution, but you can argue in other way as well. Like from here only you can look that limit x going to 0 sine of x, this limit does not exist, right? Okay, so now what you can do is, so maybe this is the first kind of solution, this is the second. Okay, so what you can do now is, so assume, so you have to prove that this limit exists. Okay, so you can do it by contradiction. So you assume, so assume that the limit exists. So limit x going to 0, x plus sine of x exist. Okay, then this, and you also know, limit x going to 0, x is going to be 0, right? This you know. So the difference of these two functions, so you know limit of f exists, limit of g exists, so the limit of f minus g will also exist. So this would imply that limit x going to 0, x plus sine of x minus x exist, right? So, right, so this is limit to 0 sine of x exist. So this is a contradiction, right, to this statement. Okay, so this is another way of proving that this limit does not exist. Okay, so I'll just, so why I told this proof, so there's a thing that I wanted to mention. Let's see, you saw this particular thing, right? Over here, just notice this one. So what you observed that the product limit existed. Okay, we have seen an example where the product limit existed, one of the limit existed, but the other one does not exist. But in case of summation, this is not true. Okay, so now if I ask you a question, so this is maybe that suppose if limit x tending to 0 or extending to c, f of x plus g of x exist, and limit x tending to c, f of x exist, then limit x tending to c, g of x exist, then this statement is true, right? Because if this function limit exists, this function limit exists, you just subtract it, you will get that this limit exists due to this. So you know this formula, right? This theorem, you know that the sum of limit of two function is equal to the sum of the individual limit, right? So using this, you can get this result. Plus or dot, minus dot. This is plus, minus and dot multiplication. And even the thing is true for division as well. If a function in the denominator the limit of that function should not be 0. So if the limit is non-zero, then it's true for the division as well. Okay, so this is the remark that I wanted to mention. So over here you can clearly see that this limit, if you assume that this limit exists and you already know that this limit exists, then that will force that the limit of this exists, but you know very clearly that this limit does not exist. Okay, I hope that was clear to everyone. Now let's move to this problem. Okay, so again over here you have to use the definition of the limit to prove this, that the limit x tending to 3 of this function is going to be 3. Okay, so again we'll proceed in the same manner as was done for the first problem. Okay, so you have to choose any epsilon. So let epsilon greater than 0 be any number. What you have to do is you have to estimate the difference of the function with the limit, correct? So now I will try to look at this term, 2x plus 3, 4x minus 9 and minus 3. So just simply take the limit, you just take the difference, and then you have this 2x plus 3 minus 12x, and then you have plus 27. So over here you have minus 10x plus 30 upon 4x minus 9, which is equal to, so 10 you can take outside, so you have 10 upon mod of 4x minus 9 times x minus 3, right? So see, we have got x minus 3 for this term, right? So now the only thing what we need to do is we have to bound this term. So if we can get a constant, that means if we can get rid of this x from here, then we are done, correct? So that is the only thing that we need to make sure. So what we will do, again, like as we have done before, we'll try to look at some particular range for x. So what values I should choose for my x so that this whole term become bounded or can be bounded by some positive constant. Okay, so suppose, so we have to look x in the neighborhood of 3, right? So that is one of the thing, that we have to look for x in the neighborhood of 3. Now what if I choose x from 2 to 4? So if I am choosing the neighborhood 2 comma 4 for 3, how will this 4x minus 9 behave? So let us see. So x is from 4 and then 2, so you multiply 4x, so you will get 16, you will get 8. Now you subtract minus 9, subtract 9, so you will get minus 1 less than 4x minus 9 less than 7, correct? So now so over here you see there is one minus sign. Okay, so what you can say, but over here I wanted to use some lower bound for this. So I want some 4x minus 9 should be greater than equal to something. So if I get this kind of thing, then I can say this is less than 10 by m, right? So I want a lower bound, some positive lower bound, right? So over here I can clearly see that this is not going to give me a lower bound, right? Positive lower bound I cannot get. So what I'll do, I'll try to reduce my size. So now let us take from, so what will be the intermediate value? 7 by 2, and here I'll have 5 by 2. So if I choose my x from this thing, so let us now remove this one. So x is from 7 by 2 and then 5 by 2, multiply by 4, I'll get 10, and here I'll get 14. If I subtract 9, I'll get 1, and here I'll get 13. So now here you can clearly see that 4x minus 9 is greater than 1. So this would imply that mod of 4x minus 9 is also greater than 1, right? Okay, so we have got what we wanted. So for x such that mod of x minus 3 is less than half, we have this 4x minus 9 is greater than 1, and this would imply that 2x plus 3 upon 4x minus 9 minus 3 is less than 10 times x minus 3, right? And this is less than epsilon if mod x minus 3 is less than epsilon by 10, right? So now what I'll do again, like before, I'll choose delta as minimum of this and this. So choose delta as minimum of half and epsilon by 10. Okay, and then you are done. Then you have 2x plus 3 upon 4x minus 9 minus 3 is less than epsilon if 0 less than x minus 3 less than delta. Okay, so over here actually my function is defined even for x equal to 3 if you look, right? So over here, like, even you don't need to put this, but I am writing this over here just because just to write in the same way as I mentioned the definition. Okay, but over here you don't need this. So this basically means that x is not equal to 3, but over here even if you put x equal to 3, this function is well defined, so there is no issue as such. Okay, so that's all. So was this fine? Did you get the answers? Okay, so now let's move to the next problem. So here you have to prove that, so over here a and b are given to be positive. Okay, then you have to find the limit as x approaches 0 for this function. So this is your fx. Okay, so let's see how the function behaves. So this f of x, so let me first write, this is x by a and this is b by x. Okay, so now you see what is the definition of this, so, or property of this box function. So this box function x, so this basically takes the least integer value till x, right? So if the definition of this is supremum of n belonging to z such that n is less than equal to x, correct? So this is the definition, and this x you can clearly, so when x is actually integer, it will take the value x, right? So this x will be x if you are taking the integer as the value for x. If x is not integer, that means x is some decimal value, then it will take the value x minus 1, right? So the value of x, box function x, will lie between x minus 1 and x, correct? So for example, so suppose this is 0, this is 1, this is minus 1, this is 2. So if I choose my point here, if I choose my x as this point, then obviously this box function x will be 1, right? If I choose my point here, the box function will be minus 1, right? And if I choose the function this point as this, then corresponding to this, the box function x would be again minus 1. So this is the thing, right? So if you are choosing this x as a intermediate point between two integer, then it will take the previous integer value, as in this case or this case. But when you are choosing x to be the integer, then obviously the box function will be x itself. So this is the obvious bound that you have, right? This one, very obvious one. So I'll try to use this over here. So you have this b by x, this box function is less than equal to b by x and greater than equal to b by x minus 1, correct? So from this, now what I have to, so basically I have to look at the limit. So I'll have to look at the bound for this one, okay? So now if I multiply this whole thing by x by a, so over here you have to look at this one maybe. So okay, I'll have to take two different cases. So when x is greater than 0, okay, then you just multiply this whole thing. So you will have x by a times b by x minus 1, x by a, b by x. So over here x is non-zero, okay, and this is b by a, correct? This is b by a minus x by a. So this is when x is positive. When x is negative, okay, then you will have again, there will be just change of the sign or the change of the inequality basically. So what you have is now x by a times b by x is less than equal to b by x times x by a, and then less than equal to x by a times b by x minus 1. So again this is b by a f of x, b by a minus x by a, right? So from here what you get, so if you use the, okay, I should not say exactly the sandwich theorem because there we talk about the limit, but over here we are just looking at the right hand limit. So this right hand limit is sandwiched, you can clearly see that this is sandwiched between this value and this value for positive x. So this would mean that limit x going to 0 plus, okay, x by a times b by x, this is going to be equal to b by a, correct? This is due to this, not I am saying sandwich theorem, but like the same argument. So if you go to the proof of the sandwich theorem, the argument what it uses can be used here, right? So what is the difference between the right hand limit and the left hand limit? So basically, so okay, let me mention this here. So you see, you have two things: limit x tending to 0, f of x is equal to c. So this means that mod of fx minus c is less than epsilon if 0 less than x minus c is less than delta. But when you write this term, this thing, this basically tells you that fx minus, I think I should write L here and this C, x minus L, yeah, C plus. So this means that this difference fx minus L will be less than epsilon if your x is now, if it's not going to be in the neighborhood of, it's just going to be on the right neighborhood. So x minus c less than delta means that x is from here, c minus delta to c plus delta. But now when you're talking about this right hand limit, it basically means that x should be in this interval, c plus delta, if x belong to c to c plus delta. And here it means x belong to c minus delta. So this means x belong to c minus delta to c plus delta, right? So this basically means you are just looking at the right hand limit, okay? So this proves that the limit x going to 0 plus, this is going to be b by a, okay? So kind of squeeze theorem or sandwich theorem, okay? And this tells you that the limit x going to 0 minus f of x is going to be b by a, again by squeeze theorem. And this, both the statements tells you that the limit exists and the limit value is b by a. Okay, so is this okay to everyone? Is this fine? Okay, so now we'll move to the next problem. Is this limit x going to 0? Okay, so now let's move to the next problem. So this is the function. Okay, so fx is equal to x when x is rational, and it's 0 when x is irrational. Okay, so you have to find the value of this. So basically you have to prove whether this limit exists or not. Okay, and if it exists, what will be the value? Okay, so let's come to the first problem, the limit. So let's look at the neighborhood of 0. So what do you think? What is your intuition saying? So over here, see, the function is same, only you are changing the point where you are taking the limit, right? So what do you feel about the limit? Okay, so as one of you mentioned that this limit will exist but this will not, right? So before going to the proof, let's look why this is happening. So you see, if you look at the neighborhood, okay, so suppose this is in my x-axis, this is 0. So how the function is behaving? So for rational, this is x. So this, so suppose if this is my point x, then this is the function value. This is my point x, then this is my function value, right? So it's like basically it's lying on this line, right? Y equals to x. So this is the line y equals to x. So your function f is oscillating between this and 0. Okay, so these are not there will be discrete points, and here also there will be discrete point, right? So the function is either 0 or in this line, on this line, right? Because of the density you cannot draw it, but this is how it looks. It is oscillating between 0 and x. But in the neighborhood of 0, if you see, in a very small neighborhood of 0, it is very close to 0 only, right? Because even if you take x, this straight line, the red straight line, is also in the neighborhood of x, right? So this is why the limit exists. Okay, whether it's 0 or whether it's taking the value x, it does not matter. But now when you look at this point 1, okay, now over here how the function behaves, either this is 0, right, or the function is taking the value on this straight line, where they are very far away from each other, right? So once the function is here, once the function is, and the next moment the function is here. So when the point x is rational, the function value is far away from 0. okay, and when the function value is when the point is irrational, the function value is 0. So you see there is a huge gap between the function value. So I mean, you cannot see that how it converges to one point. The function is very oscillatory in the nature. So you cannot expect that it should converge to some fixed point. Okay, so this is uh, the main idea. Okay, so now we'll just write a bit of language. Okay, so let's prove. The first part is easy, right? So my claim is that limit x tending to 0, f of x is going to be 0. So this is my claim 1, maybe. Okay, so let's prove this claim. So over here, let epsilon, again the same language. So let epsilon greater than 0 be any number. Okay, so now I'll take the difference between fx and 0. So this is mod of fx. So what is the value f is taking? So it is mod x if x belong to q, and this is 0 if x belong to r minus q, right? Now obviously this 0 is obviously less than epsilon, right? Because epsilon is positive, and this is also less than epsilon if my x is less than epsilon. Like, this is very obvious thing to write, but you can understand what I mean, right? So overall what I can say, that this mod of fx minus 0, mod of fx minus 0 is less than epsilon if mod x is less than epsilon, which is the delta. Okay, so let me write in this way. Okay, so you have got a delta which is same as epsilon, such that if your mod x is less than delta, then fx, so this mod x basically means mod x minus 0, right? This I should mention. So this 0 is the limit, this limit point, and this is the limit value 0. Okay. So this proves the claim. Okay, so this was very easy. Now coming to the next part. So my claim is that limit x going to 1 f of x does not exist. Okay. So how to prove this one, that it does not exist? So the proof, what we'll do here is basically the proof by contradiction. So we'll assume that, okay, let the limit exist, then we'll try to contradict the definition somehow. Okay, so let's see. So suppose, if possible, limit x going to 1 f of x exist, and let I mean this limit, let L, so I'm putting the limit value to be 1 L. Okay, so we have fixed that, okay, this is my limit value. So now I'll try to write it in the 3 different cases. So when L is positive, when L is 0, and when L is negative. Okay, so let's start with L greater than 0. Okay, so now when you take L to be greater than 0, I can choose my epsilon using L, right? So what I'll do is, so now I have assumed that this limit exists. Keep in mind that the limit f exists, and that is equal to L. So now when L is greater than 0, so for epsilon equal to L by 2, there exists delta greater than 0, such that this mod of fx minus L, right, I am using the definition, is less than L by 2 if 0 less than mod of x minus c less than delta. So this is by definition. Okay, just the definition. Now what does this mean? This means that the function f is lying between L by 2 and 3L by 2. Correct? Now over here, yeah, okay, so now I will try to break this in this way. Okay, over here C was 1, right? So let's write it in this fashion. C is 1. So this means that x belong to 1 minus delta to 1 union 1 to 1 plus delta. Okay, although I don't need it, but okay. So now the question is, see, this function value, if you look at the definition, this function value becomes 0 when you choose irrational point, right? Now in this interval there are many irrational points. So this means for for x belonging to whatever interval you choose, 1 minus delta comma 1 union 1 to 1 plus delta, if you choose the irrational point r minus q, right, f of x is equal to 0, correct? So from here this implies that this function value is 0. That means L by 2 is less than 0, less than 3L by 2. But this is absurd, right? Okay, once you are saying, okay, so if you don't want to write the second word, from here only you get the contradiction. This tells you that L is less than 0. But here you have assumed that L is positive. So this is a contradiction, right? So what I have done, I have just used the definition. So when L was greater than 0, I chose my epsilon to be L by 2. And this I could do because L I know is positive. So I can choose L by 2 as my epsilon. Okay. Now corresponding to this epsilon, I got a delta for which this definition holds true. And this implies that fx will lie between L by 2 and 3L by 2. And this proves that when you take x to be an irrational value, then it will give you 0. So this tells you that L is negative, which is a contradiction. Okay. Okay. So now we'll come to the second case where L is equal to 0. In this case, I'll have to choose some epsilon, okay, and then we'll try to contradict. Okay. So now when L is 0, so you have to check this the value of mod of fx. You will get the estimate of this one, right? So for epsilon, so just again by definition, so for epsilon greater than 0, there exists delta greater than 0 such that mod of fx is less than epsilon if 0 less than mod of x minus 1 less than delta. Correct? Now over here, so this basically means, I'll just write one more line, minus epsilon f of x less than epsilon if x again belong to 1 minus delta to 1 union 1 to 1 plus delta. Okay. So this is the estimate what you have on function f. Now to get a contradiction, okay, you have to choose this epsilon in such a way that you get a contradiction, right? Now you notice one thing. So again, if you take rational from here, if you take rational from here, you will get the value 0. But when you take irrational, you will get the value x. Okay. So for x belonging to, okay, just one second. So what you do in this interval or in this interval, there are many rational points that you know. So for no, I cannot say because delta I don't know, but okay, so let me again go with this. So for x belonging to some 1 minus delta to Okay, let's take the right interval. So 1 to 1 plus delta. Then what does this mean? I am intersecting with q. Okay, then my fx is going to be x, right? And this, because I am choosing x from here, this tells me that it is greater than 1, right? Now if I choose my epsilon to be less than 1, then that is a contradiction, correct? So for example, let's choose epsilon to be half. So for epsilon equal to half greater than 0, okay, you get epsilon equal to half, you write here half, you write here half. So this tells you that if I choose my x in this domain, then my function value is always going to be less than half. This is what the definition tells you. But if you choose your x from this interval, okay, then what you are getting, and if you intersect with rational, so if you choose rational number from this interval, then the function value is actually greater than 1, right? So this is a contradiction. Here you are saying that the function value is less than half, here you are saying that the function value is greater than 1 for some x, right? So which is a contradiction. So this is a contradiction. Okay, so L is not possible. I mean L equal to 0 is not possible. Is this okay? Are you really getting it, or is it just me who is just saying something? You can tell me if you are facing some problem. Is it okay so far? It seems there is some problem. You can tell me what doubt you have, then I can tell you. Let me know your doubts. Okay, it's okay for one of you. No, is it becoming too complicated? So see, like, okay, I'll repeat it again. So my claim was that the limit does not exist. Okay, so now I'm saying that to prove this, I'll assume that okay, let the limit be exist. So I'm proving by contradiction. So I'm assuming that okay, let the limit exist and let it be L. Okay, now I said that case 1 is suppose L is positive. Okay, then using the definition, I got this line that my function is greater than L by 2 less than 3L by 2 if my x is in this neighborhood. Okay, now when x is irrational, I am getting the functional value to be 0. So when I choose x from this interval which is irrational, I am getting fx is 0, and this is telling me that L is negative, and this is a contradiction because I am assuming that my L is positive. Okay, fine. Now when I am choosing L to be equal to 0, okay, in that case I chose epsilon to be half, for example. So why I chose this half, I told you, like how I am getting this half. So I am getting this half from here basically. So if you choose any epsilon which is less than 1 will work. Okay, so for epsilon equal to half, I got that the function is lying between minus half and half if my x is in this domain, right? Now when I am choosing x from here which is rational, then I am getting the function is greater than 1, right? And this is a I mean these two statements, what I made here and what I wrote here, are contradicting each other. So this is also not possible. Okay, now case 3 is when L is negative. Okay, but actually if you see, you don't need to address this case. Okay, so I'll give you one reason. So see, as I mentioned here, so how is the function defined? So you are looking at a neighborhood of 1. So you are looking here at this point. In this region, you can clearly see that fx is always greater than equal to 0 when x is in this, let's say 0 to 2. So when you are taking a one length neighborhood of 1, then in 0 to you can see that fx is greater than equal to 0. Then this would force you that if you take the limit, so suppose the limit exists, then this limit L is always going to be greater than equal to 0. Okay, so I just want to contradict this one, that this is not possible, that limit will exist. But if the limit exists, then it has to be greater than equal to 0. Okay, so case 3 does not even make sense for this particular function, but over here we'll do it. Okay, just because I don't want to use this kind of reasoning. Okay, so I'll disprove the case that L is negative as well. Okay. Okay, so now let's come to the case 3 when L is negative. Okay, so again, so just like the first case, I'll try to choose epsilon using L. So now I can choose epsilon to be minus L by 2. So for epsilon this, there exists delta greater than 0 such that this fx minus L is less than minus L by 2 for x belonging to 1 minus delta 1 union 1 plus delta. Okay, and what does this mean? So this basically mean that fx is L by 2, 3L by 2 less than fx less than L by 2 for x belonging to 1 minus delta 1 union 1 plus delta. Okay, again, so what we have got using the definition that the fx will lie between these two values. Okay, when I choose x from here, again, if you choose x, okay, such that x is in this region, but x is irrational, I guess irrational, it was 0, correct. See, if I choose irrational point from here, I'll get this value to be 0, right? And if I use this inequality, it tells you that L is positive, correct. So for x belonging to 1 minus delta 1 union 1 comma 1 plus delta, if I intersect with this r minus q, then fx is equal to 0. So from here what I get is 0 is less than L by 2. So this proves L is greater than 0, which is a contradiction, right? So again, this is not possible. Okay, so this case 3 is basically similar to what we have done for the case 1. There is nothing new over here. Okay, so now let's come to the next problem. Okay, so the problem is that suppose you have a real valued function from R to R, okay, which satisfies this property. So what it tells that f of x plus y is equal to fx plus fy. Okay, so this function is satisfying this property. Now you have to show, so you have to assume that, okay, that the limit exists. Under the assumption that the limit exists, you have to prove that the limit value is going to be 0. Okay, so one thing is given to you, that the limit exists. So don't have to worry about the limit. The only thing what you have to work for is that what will be the value of the limit, right? Okay, so so have you seen this kind of problem before, like where you have this kind of property? Again, there is some lag, I feel. Okay, so have you seen this kind of property earlier?
Linear.
Okay, so you are talking about this, correct? This is a linear function, what you are saying. Okay, but yeah, what you are saying, okay. No, exponential function is not going to satisfy this, right? So e of x plus y is equal to e of x times e of y. Over here you have plus, Okay, so exponential is not an example. Okay, but what she said is some way okay, that okay, it's from here you cannot prove it's linear because it has to satisfy this multiplication, a scalar multiplication as well, but okay, okay, no issues. So now what I was saying is, so using this property you have to deduce something, right, so that you can go for finding the limit value. Okay, so one thing you note, okay, so let me first, if you put x and y to be 0, okay, so put, so let me call this line as a star, so put x equal to y equal to 0 in star. Okay, so what do you get? So f of 0 plus 0 is equal to f of 0 plus f of 0, and this is again f of 0. So from here what you can deduce is 2 f of 0 is equal to f of 0. If you subtract it, you will get f of 0 is equal to 0, right? Yeah. Okay, I have one question. So from here, like from here we got that 2 of f0 is equal to f of 0, right? So from here can you say that f of 0 will be, okay, you cannot conclude anything. Okay, fine. Yeah, so f of 0 is equal to 0, fine. Now the other thing is, what if I put y equals, so we know the value of f of 0 from this property, we got that f of 0 is going to be 0. Now what if I put y equals to minus x in this star? Okay, so if I put y equals to minus x, so I will get f of x minus x is equal to f of x plus f of minus x, right? Now you know that this is f of 0 and this is 0, so this tells you that f of minus x is equal to minus of f of x. Right? Now I think the answer should be clear to you. So see, you have been given that this limit exists. Okay, so you have to use this fact that limit exists. Okay, so now what I'll do, if I take limit x going to 0, then what I get is limit, yeah, it's an odd function, correct, you're right. So this tells you that f is odd function, but okay, I won't be using it, but this tells you that this f is odd function. Okay, so now what I was saying is, if I take the limit both sides, so what I get is limit x going to 0, f of minus x is equal to minus of limit x going to 0, f of x. Okay. Okay, so clearly, so this so over here I had, okay, no issues. Okay, so this, let me say this is star. Okay, now what I'm saying, look at this term. Okay, so this tells you that limit x going to 0, f of minus x. So over here, this x going to 0 means minus x is also going to 0, right? There is no issue as such. So I can say this is minus x going to 0, f of minus x. Again, if I do a change of variable, so if I put y equals to minus x, then this tells you that limit y going to 0, f of y, right? Okay, now if I put it in star, so this, so what this whole thing is telling you, so this whole thing tells you that this is nothing but limit x going to 0, f of x, right? This is what it tells, correct? So now if I, now there is no put star, so now if I just add, take this to the left hand side, this one, So what I get is 2 times limit x going to 0 f of x is equal to 0, and this tells you that limit x going to 0 f of x is 0. Right? So you have got the answer. Okay, but see over here I have not proved that the limit exists. So here I have used this fact. So I have assumed that the limit exists. If I remove this assumption, then the problem is going to be very difficult, and even I don't expect that that just using this property, I don't think someone can tell that this limit will exist. Okay, so you have to assume this condition. Okay. Okay, now let's come to the next problem. So over here you have to compute the limits for the following function. Okay. So let's begin with the first one. So what do you think? It's a very easy problem, right? I think I mentioned it also. So can you tell me what will be the limit value of the a?
0.
0, right? Yeah. So how, just like how I mentioned earlier, that if you take x, so cos 1 by x, this is bounded by mod x, and this is less than epsilon if mod x is less than delta, which is equal to epsilon, right? So this tells you that limit x going to 0, x cos 1 by x is going to be 0. Okay. Okay, what about the second one? So over here I am just, so let me first write. So see, 1 by x, if I put minus, then this will go to, so as x goes to 0 from the right hand side, okay, that means x is positive, so this will go to minus infinity, right? And if I take minus 1 by x, so this as x goes to 0 plus, and this will go to infinity if x goes to 0 minus, right? Okay, so the answer is obviously 0, as he mentioned. So this as goes to minus infinity, so e raised to the power minus infinity, so this is not a correct thing to write, but what I am saying that this is very exponential of a 1 upon exponential of very large thing. Okay, so infinity means like it's going to increase, so this will eventually go to 0, right? So the answer is 0, but you cannot, if you want to talk about this limit, I mean the limit of this will not exist. Okay, so right hand limit is going to be 0, left hand limit, if you look, it is going to be infinity, like it will explode, so it is I mean the limit is going to be infinity if you take x from left hand side. Okay, so the limit does not exist, but the right hand limit exists, and that is equal to 0. Okay, now the question is how to prove it. So let's look at the proof. Okay, so you have e minus 1 by x. Okay, so this, this is always going to be greater than 0, right? Exponential function is always going to be positive function. Now you have to find some bound, right? So can you tell me some bound for this one? Do you have any idea? Yeah, it is obviously less than 1, but this will not give you any result for the limit. So I am expecting you to tell me some bound from where I can use that to conclude that the limit is going to be 0. So I think I discussed in the last session, right, that what are the bound on the exponential function. We have very obvious bounds. Okay, so you know this thing, right? E of x So for x positive, so what is this? So 1 plus x square by factorial 2 plus so on, right? So this is greater than equal to x if x is positive, right? It's very obvious because all these terms are positive. No, 1 by x will not work. No, you are. So see, okay, I'll come to it. So if suppose you got 1 by x, then you are getting a wrong answer, right? Because as x goes to 0, this will explode, this will go to infinity. So that is, even if this is true, you cannot get the result, right? Okay, so now let's see. So using this, what I can say is e raised to the power 1 by x is greater than equal to 1 by x, right? Now you take the reciprocal, so what you get is e minus 1 by x is less than equal to x. So everywhere x is greater than 0, right? So you got this bound, so you can plug it here. So see, this is where x greater than 0 is used, I mean the right hand limit. Okay, so this is true for x greater than 0. Okay, so this is where the right hand limit comes into the picture, because for negative x you cannot get such bound. Okay, so this will tell you, so this implies limit x going to 0 plus e minus 1 by x is going to be 0 by squeeze theorem. Okay, so this was about the b part. Now let's come to the c1. So you have to find the limit for this function. Okay, so this looks quite complicated, so let us write what the function is, then we'll look at the then we'll talk about the limit. Okay, so this was box function x minus box function x by 3. Okay, so let us see that we want to determine the limit of this function as x approaches 3, right? So what we'll do, we'll look at this function only in a neighborhood of 3. So let's take the maximum, I mean let's take the interval of length 2. Okay, so for x equal to 3, the interval of length 2 should be the 2 comma 4, right? So we'll look at, so when x is from 2 and 4, okay, so we'll look the function value in this range, in this domain. Okay, so what will the function value when x is in 2 comma 3, let's say. So when x is in 2 comma 3, this will give you 2, right? So I'm not closing 3. Okay, so in this 2, and then here you will have, so x is not equal to 3, so it is always going to be less than 1, right? And it's always going to be positive. So in this region x is less than 3, so this implies, and greater than 2, so this implies that 2 by 3 is less than x by 3 less than 1, right? So x by 3 is always going to be lying less than 1, so this box function will give you value 0, correct? Now when x is in 3 comma 4, so let's close this 3. Okay, open this 4. Then in this case, this box x will give you 3 and this one will give you 1, right? Because x, so in this case x is greater than equal to 3 implies x by 3 is greater than equal to 1. Okay, and x is less than 4 also, so let me write this, 3 less than equal to x less than 4. This tells you 1 less than equal to x less than 4 by 3, correct? Just a second. Yeah, 4 by 3. So let's restrict a bit more, because see, this is going to be 1 point something something. Yeah, then it's okay. So this is x by, sorry, this is x by 3. So x by 3 lies between 1 and 1 point something something, so which is less than 2, correct? So this x by 3 is always going to be will always take the value 1. Okay, so this is this box x by 3. So ultimately what you have is this function f is constant 2 for, so f of x is equal to 2 for x belonging to 2 comma 4, right? Now you can clearly, from here you can clearly say that limit x going to 3, f of x is going to be 2. Okay, so this is the answer. Okay, so now let's come to this d part. So d part tells you to tell the limit of log 1 plus x. Okay, so over here this log basically means the ln. Okay, so this log, I should mention this log is with base n, so this is nothing but ln. Okay, okay, so d part is limit x going to 0 ln 1 plus x. Okay, again if you see, if you know the property that this log function at 1 it will be 0. Yeah, answer is correct. So the limit is going to be 0, correct? Now the question is, so see this, all this limit question becomes very easy once you know this. Okay, so over here it's, you cannot use L'Hopital, but I think at some point can you use, okay, in these problems 0 times, so over here this L'Hopital is not needed, but okay, fine. So what I was saying is that this log function, you know that at 1 it is going to be 0, and now as you take the value, if log at x, log of x will be negative when x is less than 1, and it is positive when x is greater than 1, correct? So this log function is just, so log of x is going to be 0 if x is equal to 1, it is going to be positive if x is greater than 0, negative if x is less than 1. So because of this kind of behavior, we'll try to calculate the left hand limit and right hand limit separately. Okay, so the first thing is, so you assume x is greater than equal to 0. Okay, now once you assume that x is greater than equal to 0, you can say this is 0, because I know when x is greater than equal to 0, that means 1 plus x is greater than equal to 1, right? And when x is greater than equal to 1, I know that my log function is positive, so I can use this thing, right? So ln 1 plus x is greater than equal to 0. Now we'll have to look for some upper bound, correct? So again, like I'll use the same bound. So as I mentioned that e of x is greater than equal to, so let me first write 1 plus x square by factorial 2 and so on. For, so when x is greater than equal to 0, I can write this as 1 plus x if x is greater positive, right? So I have this bound. Now if I take log, I'll get x greater than equal to log of 1 plus x, right? So from that I can bound it by x, right? Again by sandwich theorem, this will tell you that limit x going to 0 plus ln of 1 plus x is equal to 0. Okay, so you got that the right hand limit is going to be 0. Now let's look at this limit value when x is negative. Okay, so when this x is negative, so now what you know is this ln of 1 plus x is also going to be less than equal to 0. Okay, so one side is clear that it is going to be negative. Now what about this lower bound? So I want some lower bound here, right? So that I can use the squeeze theorem to get my limit value, correct? So what I'll do here is, okay, so I'll first write what the bound is. So it is basically x raised to power 1 by 3. You can use this bound. You can use x raised to power 1 by 5 as well, 1 by 10, whatever you want. You can use it. And the proof for this bound is very easy. Like you just take fx to be, okay, have I mentioned fx here? No, no, so it's fine. So ln of 1 plus x and minus x 1 by 3. Okay. So you can clearly see at x equal to 0, this is 0. Okay. So what I'll prove, so f prime x, if you see, it is 1 by mod 1 plus x and then minus 1 by 3 and 1 by x 2 by 3, right? Okay, so this is the bound what I have. Now what you have to prove is that if I can show that this is greater than equal to 0, this will tell me that my function is increasing, right? And so this fx, just a second, should I expect to be increasing? Because suppose if I say it is increasing, then it has to be less than equal to f of 0 if x is less than 0, right? This is what increasing means, but then this will not give me the bound, right? So I have to prove this is decreasing, sorry. Yeah. So if I prove that this is negative, then I can say this will imply that f is decreasing. Okay, decreasing where? So that is also a point. So suppose I show that this is less than 0 in some domain, then this will tell me that f is decreasing in that domain, correct? So obviously it has to be open interval 0, that is for sure, correct? Because I am choosing my x to be strictly less than 0. Okay, now once I prove that it is decreasing, that would mean that if I increase my x, so if x is less than equal to 0, then the function value will be greater than equal to f of 0, right? And from here what I will get is ln 1 plus x is greater than equal to x raised to power 1 by 3, which is this bound, right? Okay, so now the question is how to, so we'll have to check whether it is decreasing or not, right? So let's see now. So if you look at this term, okay, so what is this term? This term is 1 upon something. So you know that 1 plus x, I can say this is less than equal to 1, right? Correct, because x is negative. So this will tell me moreover, okay, so let's restrict. So I am saying x I am taking to be from minus 1 to 0, okay, so that at minus 1, otherwise this will create a problem. Anyway, this log function, okay, so I should mention it, this is defined when x from minus 1 to infinity, right? Okay, so we anyway have this lower bound for this x. So if I choose my x to be minus 1 to 0, then this 1 plus x is going to lie between 0. So it is strictly greater than 0, and then we have this. So if I take, so this mod does not make any sense. This is always positive. So I can replace this by 1 upon 1 plus x, no issue. And then I have 1 by 3, 1 by x, 2 by 3. Okay. Now this 1 plus x is less than equal to 1. That would tell you, so this is less than 1, and this quantity, so what you have to do is, so when x is less than 1, if I take the square, it will reduce the size. Okay, let me take the LCM. Just let me see. I think let's take LCM, then I think it should be more easier. So this is 1 plus x, so mod does not make any sense here because it is positive, so I have this. Now if I take the LCM, I'll get 1 plus x, here I'll get x 2 by 3. Okay, here I'll get 3 x 2 by 3 minus 1 minus x. Okay, so minus of 1 plus x, correct. Okay, let me write this term minus x minus 1. Okay, now I think it's easy. Okay, so I don't think we have to deal with this, sorry. So now look at this term. This term, okay, this you can think as this, that x square and then you take 1 by 3. Okay, so now this is a positive quantity, right? And then you are taking 1 by 3. But the main thing is that this x, you are looking at very close neighborhood of 0. Okay, so I am assuming, so it's better to write that I am choosing my x in a very small neighborhood, so minus epsilon to 0. This has to be small so that this whole thing turns out to be negative. Okay, because I know that this two quantity, if you look at these two quantity, this is positive, right? Because x is positive, I mean x is negative, so minus x is positive, and this as I already told you that this is positive, but I want to make this quantity very small, right? So first thing is that this is a positive quantity. Okay, so if it is greater than 1, then this is going to be a positive quantity. Okay, so that's why I am restricting my x to be very small. Okay, so I am choosing x in a very small neighborhood so that this whole quantity is very small, and hence this minus 1 will dominate to make this numerator negative. Okay, so what I can conclude is this is less than 0 if my x is in this minus epsilon to 0 for sufficiently small epsilon. Okay, so I'm choosing epsilon very small so that this numerator is negative, and I hope you can understand that this, if I choose my epsilon to be very small, this whole thing will turn out to be very small, right? There is no doubt this 3 is not going to create any problem, right? That is very obvious. Okay, so I'll get this derivative as negative. Now once this derivative is negative, so what I can say is, why I am rubbing this one? So now what I can say is this implies this implies f is decreasing in minus epsilon to 0, right? And this will tell me that f of x is greater than equal to f of 0 if x belong to minus epsilon to 0, right? And this will tell me that this ln 1 plus x is greater than equal to x raised to power 1 by 3 for x belonging to minus epsilon to 0. Okay, so this bound, what I am writing, this bound is not true for any x negative, but this is true for x belonging to minus epsilon to 0 for sufficiently small So see, this is one of the bound that I have found, but you can get many other bounds as well, maybe better than this. Okay, so I just chose this because I want this for my problem, that's it. Okay, so this proof is here. Okay, now it's very easy. Again, by squeeze theorem, you can say that limit x going to 0 minus f of x is 0. Okay, so hence by this 1 and 2, 1 and 2 gives you that limit x going to 0 f of x is 0. Okay, so again I am saying that there could be other proof which might be better than this one. Okay, but this is what I got. So okay. Okay, so now let's move to the next problem. So you have to prove that these limit exist and this is equal to the value given here. So I think time is almost there. Let me see what is the 10th problem. Mm, this seems to be more interesting. So I think you already know these two at least. Oh, okay, but this was interesting. Okay, let me complete this. If time permits, I'll go for the 10th one. Otherwise, I'll discuss in the next session. Okay, no issue. Okay, let's come to this one. So the first thing is that limit x going to 0, sin x by x is equal to 1. And this is where you can obviously use the L'Hopital and you can get the answer. But over here, we'll try to prove it using the squeeze theorem and all. Okay. So over here again we'll try to use the bounds to prove this kind of limit. Okay. So you see you okay, so there's one interpretation what I don't know whether you know it or not. So what does this mean? Okay, that this limit x going to 0 sin x by x is equal to 1. See, if you look as, so you must have heard something like if one of the function is bounded and one of the, like this kind of thing. If you look here, this sign is a bounded function, right? So as x goes to 0, this should go to infinity, if you think in that way, because one of them, so if I remove sin x by 1, okay, if I remove sin x by 1, then it is going to infinity, right? But this sin x by x is if I consider it as a ratio, then it is, if you look, sin x is going to 0 as x goes to 0, this is also going to 0, so this is a 0 by 0 form, right? So the point is, what does this mean, that this limit of this ratio is equal to 1? What does that mean? So suppose if I remove the limit thing, if I tell you that this sin x by x is equal to 1, then this, you will say clearly that sin x is equal to x, right? This is a very obvious thing. Now when it's in the limit, it means that sin x is almost equal to x when you are in a very small neighborhood of 0. So what it means, so the value of sin x and x are very close in a neighborhood of 0. Even if you look at the graph, you see this sin x goes like this and this function x goes like this, right? I mean, okay, I have not drawn it properly, but you can understand what I am trying to say, that these two graphs are very close, near 0. So in this neighborhood, you will see that these two graphs are very close to each other. So they are almost same in a neighborhood of 0. Okay, so this is what it means. Okay, fine. Now let's come to the proof. And this reason what I was telling you before, that this sign is bounded function, right? Now this, as x goes to infinity, this will obviously go to 0, right? So as for large x, sin x is something which is bounded. Okay, so so there, this, even if you look at the graph, like sin x is always going to be in this, like this, and x is going like this. So this is going to infinity, but this value is always less than 1. Okay, so using that thing, you can say that this limit is going to be 0. Okay. Okay, so this is something why I'm saying this will give you a bit of intuition of understanding the limit. Okay. Okay, now let's come to the proof. So see this, I don't know whether you know this or not, but this sin x, okay, here only I draw it, the picture. So sin x is like this. Okay, so you can clearly see this is the graph y equal to x, and this is the graph y equal to sin x. Okay, clearly sin of x is less than equal to x over here in this x, when is x is greater than equal to 0. If you look here, here you see x is less than equal to sin x in this region. Okay, so actually you can prove it. So I'll just write it here maybe. So for x greater than equal to 0, sin x is less than equal to x, and for x less than 0, sin x is greater than equal to x. Okay, but you can actually prove it. How to prove it? Again, the same idea. You define fx to be sin x minus x. You take the derivative. F prime x would be cos of x minus 1, and you know this cos of x is always going to be less than equal to 1. So this is going to be less than equal to 0. This means that f is decreasing, right? And this will mean that f of x is less than equal to f of 0 if x is greater than equal to 0, and f of x is greater than equal to f of 0 if x is less than 0, right? And this will give you this estimate that sine of x is less than equal to x if x is greater than equal to 0, and sine of x is greater than equal to x if x is less than equal to 0. Okay, so the proof of this is this. Okay, again, like, so see, in one case you got the upper bound, in one case you got the lower bound. So again you have to, okay, so I will not prove this one. You can try in the same way. So how I have proved this one, in the same line you can prove this also, that for x greater than equal to 0, sorry, sin x is greater than equal to okay, no, sorry, not sin x. Okay, just a second. So I want sin x by x, so I will take x. So you can see that x is less than equal to tan x. Okay, and for x less than 0, x is greater than equal to tan x. Okay, so now I will combine these two. So I will get x is bounded below by sin x and x is bounded above by tan x. Now I will take the reciprocal and do the multiplication. Then I will get this sin x, estimate for sin x by x. Okay, so let's see. So for x greater than equal to 0, we have sin x less than equal to x less than equal to tan x. Now just take the reciprocal. So I'll get 1 by sin x, 1 by x, 1 by tan x. Okay, so this is when x is non-zero, or okay, so see, I am looking at x going to 0. So now I'll just look at x belonging to minus pi to pi. Okay, so maybe I'll mention here x belonging to minus pi to pi minus 0. Then only I can take the reciprocal. Okay, and then I will multiply by sine. So I'll get 1 less than equal to sin x by x less than equal to 1 by, so sin x by cos x, so cos x. Okay, so I think it's better to do the multiplication and then take the reciprocal. Anyway, it doesn't matter. So you got this bound. Okay, now you can clearly see this will imply you that limit x going to 0 plus sin x by x is equal to 1, right? Now for x less than equal to 0, what you have is tan x less than equal to x less than equal to sin x. Now you divide by sin x, so tan x will become cos x, sorry, sec x. Just a second here, what take it? Okay, here it's fine. Yeah. So I'm dividing by sine, so I get 1 by cos x by sin x less than equal to 1. Again, my x is in minus pi to pi minus 0. Okay, and this will give you that 1 less than equal to sin x by x less than equal to cos x. Just a second, here I did a mistake. So when I take the reciprocal, I should interchange reverse the inequality, right? So here you will have okay, there is one more thing. So okay, so here I am taking x from 0 to pi. Just a second. Okay, because see, here I am multiplying by sin x, but when x is less than 0, sin x is negative, so that would again reverse the inequality. but here I'm choosing x to be positive so that the sign is also positive. Now if I do the multiplication, I will get this. Okay, now I think it's fine. Here I'm taking x to be from minus pi to 0. Okay, so here I'll have so here what I did, I divided by sign. So here again the inequality will reverse, correct, because 1 by sign is negative. And now again I I took the reciprocal, so I'll get this. Yeah, so this will again tell you that limit x going to 0 minus sin x by x is equal to 1. Okay, just check it once. I think I have done it correctly, but there might be something mismatch. Okay, so we got, so this 1 and 2, hence what we got is limit x going to 0 sin x by x is equal to 1. Okay, now the second part, this one is quite easy. Okay, so I'll just write one line, then I think it will be obvious. Okay, so see this sin x, so you have to prove that limit x going to infinity sin x by x is going to be 0, right? So as I mentioned, that sine is my bounded function, so sine is going to lie between 1 and minus 1, right? Now when you divide by x, so this is this, right? So this is x is non-zero, so x is greater than 0, let's say, because we are looking at x going to infinity. Now you see no, this is not a good bound, so this will give you infinity and this will give you minus infinity, so this is not going to help. Oh sorry, x, correct, this is fine. So now limit x goes to infinity, if you do, this is going to 0, this is also going to 0, so this intermediate thing will also go to 0 by squeeze theorem. Right, so this was easy. Okay, now let's come to this box function of sin x by x. So limit x going to 0 okay. So see what I told you over here, like when I was talking about this part a, I was telling you that sin x is like x. Okay, sin x is almost, the value of sin x is almost equal to x when you are in a neighborhood of 0, but you have also seen this bound, that sin x is less than equal to x, right? You have seen this bound. So now using this bound, what you can say is that in fact you can note that sin x is equal to x for x equal to 0. Otherwise sin x and x are completely different function. Okay, I mean the value will not match. Okay, so this is something that you have to, I mean you will have to establish it. So but anyway I'll just write in short. So okay, so what I mean is, so let's talk about when for x, okay, when it's in 0 to pi. Okay, now when sin x is over here, as I already mentioned that sin x is less than equal to x, but in fact you can prove that sin x is strictly less than x, okay, in this region. And this is something you can prove again by same thing, that you show, you define fx to be sin x minus x, and you will see that f prime is strictly less than, or yeah, less than 0 if x is in 0. So I think I proved it here itself, right here. So you see this derivative is going to be strictly less than 0 if x is not equal to pi, right? So this is strictly less than 0 if x belong to 0 to pi, because cos x is not going to be 1, it is always less than 1 when x is in this neighborhood, and in that case you will get decreasing strictly. Okay, now when you got strict increasing, you will get this as less than, greater than, this, everything will be like this for x less than. Okay, so you have this, so I'll just write this, I think I proved it. So this is again like from above you can get sin x is less than x, right? And this will prove you, this will tell you that sin x by x is less than 1, right? Similarly, okay, one more thing, and also when x is greater than z in lies in this interval, then you know that sin x is positive, right? And even if x is positive, so sin x by x is positive. Okay, so what you got is sin x by x lies between 0 and 1. Similarly, for x is in minus pi to 0, okay, you see that the sin x is was above, so x is less than sin x. Okay, and this tells you, uh, yeah, so now you, if you divide by x, you will get 1 greater than sin x by x, right? The sign will interchange since x is negative, right? Okay, also you know that sin x is less than 0 if x is less than 0, and this will tell you that sin x by x is greater than 0 if x belong to minus pi by 0. So if x belong to minus pi to 0. Okay, so what again you got is 0 less than sin x by x is less than 1, right? From both the cases you got this. So for x belonging to minus pi to pi minus 0, you got that 0 less than sin x by x is less than 1, right? And this will tell you that this box function sin x by x is going to be 0 when x is in this, when x belong to this minus pi to pi minus 0, right? And this will tell you that limit x going to 0, sin x by x, this box function is going to be 0, right? So this is where, this is how you can establish this result. Okay, so what I said here, that sin x is almost equal to x, right? But here what you got to know is sin x by x lies between 1 and 0. Okay, so it's not actually equal to x, but sin x is always going to be a bit lower, right? Sin x is always going to be less than x. Okay, okay, so this box function reduces sin x by x ratio to 0. Okay, okay, so that's it for today. Maybe I'll discuss this problem in the next session. Okay, so I hope everything was clear so far. If you have some doubts, you can ask. Okay, since there is no doubt, let's stop today's session here itself. Okay, see you next Tuesday then. Bye.